Hello everyone. Today we're going to be tackling a pretty common aerodynamics problem where we have what's called a Poiseuille, well actually I don't know how to pronounce it, but it's this Poiseuille flow, and it's the plane Poiseuille flow, and what that means is that we have these two infinite horizontal plates right here, and then we have a fluid flowing through these plates. And so this is going to be a 2D representation here. And so the problem asks us to find the shear stress at the walls of the plate. So we're going to find shear stress here. And so we're given the velocity profile for the plane Poiseuille flow, right? It's going to be this parabolic shape here. And so we have u of y equals h squared over 2 rho mu, right, this first term, times dp dx times y over h times 1 minus y over h. And so here we have this is our height, right? So the height of the distance between the plates, and then we have our density, we have our viscosity, and then here this term, this is pretty important. This is our dp over dx. This is the pressure difference as we are traveling along the x direction here. And so with plane Poiseuille flow, we have a high pressure over here, and then we have a low pressure over here. And so that change in pressure is what's actually causing this fluid to be flowing to the right direction. Because with this type of flow, we have these two walls which are stationary, they're not moving, unlike a Couette flow. So this dp dx, this change in pressure where we have high pressure and low pressure, this is what's causing our fluid to be flowing. And then here we have y, which is just the, you're going upwards in the y direction as you go up towards the top of the plate. And if you notice, this h here is constant. We're assuming constant density. This viscous term doesn't change. And so the only thing that is changing, our only independent variable here, is going to be y. And so that should make sense because this is a fully developed flow with a no-slip condition. And what that means is that the velocity at the walls here is going to be the same velocity that the wall itself is moving. And so in this instance, we have the wall is stationary, and so at this point at the wall, the velocity is 0, and that's shown here in our velocity profile. And as we increase in y until we reach this maximum, our velocity is also increasing until we go back towards 0 as we reach the top. So we're trying to find the shear stress at either of the walls. And so the way that we do that is with this relationship. We have tau xy equals our viscosity, or viscous term, times du dy. And so if you notice, since this is an infinite plate, right, this is going off into infinity, this is going off into infinity. Nothing about this flow is going to be changing in our x direction, except for the pressure, because the pressure is what causes the motion. But the velocity here is the same as the velocity here, right? And so it is fully steady in this x direction here. And so that's why you notice that we don't have any dx terms. We're only using dy, because the velocity in the x direction, right, our velocity is traveling in the x direction, is only changing as we go up in y. So what does this here mean? This is our shear stress. And so if you look at like a single fluid element, you're going to have a, let's say this is like the bottom wall right here, right? And we'll have a small velocity right here at the bottom, right? We notice here. And then we'll have a larger velocity up top above the fluid element. And so you'll see that we can say that this height here, this is our infinitesimally small height, our dy, right? Small height. And then our du, which is going to be the difference in the velocity from the bottom and the top. So this is du. And so if you notice, if you go back to your like materials and statics and mechanics classes where we have a little fluid element here, right? We have our normal stresses and we have our shear stresses. And so this is going to be our shear stress, which is pulling like that, and it's going to be causing, well, I guess I drew it kind of backwards, but it's going to cause our fluid element to deform like this, right? Because we have our large velocity at the top and our small velocity at the bottom pulling at it. And we have this viscous term here. This dictates like how sticky the flow itself is. Because if the flow was totally inviscid, there'd be nothing actually pulling at this fluid element to deform it. And so this this deformation here is what we see with our shear stress. So our shear stress in xy is related to the viscosity or the stickiness of our fluid, and then the change in velocity as we're going up with respect to our fluid element. So let's take our derivative, right? We have this streamwise velocity, u of y equals negative h squared 2 rho. Well, I'm using a different term here, but it just means viscosity, times dp dx times y over h times 1 minus y over h. And so we need to take the derivative with respect to y. So all this becomes a constant. So du of y with respect to y equals minus h squared over 2 rho mu times dp dx times d over dy of, and so I'm just going to plug both of this into here real quick. We can do it in red, and we get y over h minus y squared over h squared. So we're just going to use that right here. Alright. And now we take our derivative, right? So we have derivative with respect to y. So let's write in our steps. Times dp dx times, and then we have, let's see, we have 1 over h here minus, we bring the 2 down, so then we have 2y over h squared. So now we have our derivative of our streamwise velocity. So now we can take, so this is going to be du dy equals, right, all that. So now we take our tau xy, our shear stress, equals viscosity times du dy equals viscosity times h squared over 2 mu. I'm just going to use mu. Sorry, this is rho, not mu. dp dx times 1 over h minus 2y over h squared. And notice we still have y here as our independent variable. Alright, so now you'll notice here we can cross out these viscous terms, and we are left with tau xy equals h squared over 2 rho dp dx times 1 over h minus 2y h squared. Okay, so now we have a function in terms of our velocity, we have our shear stress in terms of our du dy. Alright, and so we want to find the shear stress at the walls, right? So if you'll notice, since we have this no slip condition here, our velocity here is 0. Our velocity here is the greatest. We're looking for shear stress at the wall, which means we're going to have y equals 0, or I'll do it up here, or y equals h, right? And if you look right here, if we plug in 0 for y, we're going to end up with u of y, u of 0 equals 0, which should make sense because we have velocity equals 0 here. And if you plug in h for y, you'll end up with 1 minus h over h. This is 0, so this all turns into 0 as well, which makes sense because we have the no slip condition, right? So that's equal to 0. So what we're going to do is we're going to plug in for y equals 0, right? We're putting it at the wall. And then we have 2 rho dp dx times 1 over h minus 2 times 0 over h squared. This turns into 0, that cancels, and we're left with tau xy equals h squared over 2 rho dp dx times 1 over h. That h cancels here, and we're left with h over 2 rho dp over dx. Thank you for watching.